The greenhouse calculation begins with the assumption that the Earth is heated entirely by radiation coming from the Sun, which is an almost constant 1,368 watts per square meter. It'd be like having almost 14 100-watt light bulbs lighting up an area a meter by a meter square. However, the radiation coming from the Sun is not the only factor in determining how warm a planet is. Even as you try to apply an equation that begins with the assumption that the Earth behaves like a black body. To start with, let's say you had a black body. It has an opening in the side, 1 square centimeter in size. And you must heat the interior of that black body with light coming through that opening. Now, let's say the inside of the black body is a square meter in size. So it's got 100 by 100, 10,000 square centimeters or so. That means that any light coming in is essentially diffused by a factor of 10,000. So trying to warm up the inside of the black body from the outside is going to have virtually no effect by shining light in. That's the beginning assumption of the calculation. You're trying to warm something from the outside that essentially can't be warmed from the outside. So to start with, you've got to turn the Earth inside out to try and make this calculation work. Now, after that, there's a second problem. That is that when you try and cook something like chicken you would see at your supermarket or at your fast food rotisserie chicken outlet, the radiation hitting it to cook it is not the only factor that determines how well it cooks. You have to have a perfectly even distribution of that radiation over the surface of the chicken for it to cook the same everywhere, have the highest average cooking temperature. Otherwise, you end up with one side cooked and one side still frozen. Now, if we take that into account when we imagine a planet like a rotisserie chicken, then we can get huge differences in applying our pseudo-Stefan's law calculation to determine how warm the planet will be. We can have at one extreme a planet that has perfectly even distribution of radiation over its surface, and at the other extreme, you can have a planet that's permanently 1/2 lit and 1/2 dark. So we take the equation where we have 1,368 watts per square meter, and we would normally divide it by 4 because a flat disk, round surface, has 1/4 the area of a sphere. So we could take, instead of dividing by 4, which would be a perfectly even distribution of radiation over the whole surface of a sphere, we could say, well, we'll look at the thing with 2 halves. We'll take 2 hemispheres, one of them with its round surface always lit by the sun, and the other one always dark. Now, when we do this, and try and calculate the lit portion's temperature, it's not much higher than when we're dividing by 4. If we divide by 2 instead of by 4, we don't get an awful lot warmer on the lit portion, but we do get a lot colder on the dark portion. It essentially goes to almost 0. And when we average out those two, we end up with a temperature that's more than 100 degrees Celsius colder than we would otherwise. Something like 120 below or so. So just the speed at which a planet rotates and whether its rotational axis is inclined toward the sun so that the poles can get light part of the year makes a big difference in how the radiation is distributed over its surface, even before you add the atmosphere. The perfect case, perfectly even distribution, would require either a flat planet, a planet that's placed inside a hollowed out sun so it gets the same radiation from every direction, or a round planet that rotates on and revolves around the sun so quickly that one part never has time to warm up or cool off more than any other part. So the assumptions that you're making in order to make the greenhouse calculation look convincing are extremely divorced from reality. You essentially have to do the equivalent of assuming that the Earth is flat in order to ignore the importance of how radiation is distributed over the surface. Why then is there this attempt to de-emphasize or cover up the role that the distribution of radiation plays in the temperature of a planet? It might be because it hides the fact that when you want to make the highest possible temperature, you have to even out the extremes. And the hottest possible temperature is generated by having no differences at all, by having the same radiation received at every point and having the same temperature at every point. This, of course, does not fit in with the notion that the presumed greenhouse effect is going to destabilize the climate. If you try to warm something up, you have to make it more evenly heated, and that takes away the differences upon which weather depends. So much so, in fact, that a planet perfectly evenly heated at every point would have no weather at all as we know it. Weather depends on differences between sunlight received and evaporation and so on from one place to another. Also, as you add atmosphere to a planet, and that evens out the temperatures, you get a much different situation, regardless of what the gases are. On the moon, you might have temperatures as low as a few tens of degrees Kelvin, only, say, 40 degrees or so above absolute zero, so 40 degrees Kelvin or something. And where the sun is shining down on the rocky surface, you can have temperatures 150 degrees Celsius or so, which would be something like over 400 degrees Kelvin. So there are these enormous differences on the Earth, which is much the same difference distance from the sun, essentially the same as the moon. You don't get such wide variations. But you could have that happening even without the presumed greenhouse gases, because as an atmosphere gets thicker, it doesn't let as much sunlight in from the outside. Then, as you go down deeper into the planet, it gets more and more evenly heated. When you get to the rocky level of the planet, some of the potential differences from having a surface unevenly heated by the radiation coming out of the outside have disappeared. And it's a little bit like putting a layer of insulation around something, except that the things that we think of as insulators, like coats and quilts and so on, lose their capacity to insulate if they're compressed, because you have to have loft, you have to have fluffiness, because it's the air that really does the insulating, not the fabric. If you compress a blanket, it won't work as well. Now, our atmosphere will work well when it's compressed. By compressing the air itself, you can warm it. So these things can all happen no matter what gas you have. And perhaps that's why they're de-emphasized, or their equivalents are de-emphasized in making the calculation.